How long would you wait for a web page to load before you leave it? I'll answer the question by myself. Studies show that 50% of all users abandon a website if it loads more than 3 seconds. And the longer the site takes to load, the more users leave it. And that's the problem. Latency is that means the time between a request and display of a website or a page is one of the most important criteria of a website. But also, more and more content gets bigger and bigger. So you can use preloading to download the content before the user requests it, and so you can reduce the response time. But the question is, which page is requested next, and which content could be preloaded? Our approach is we use a prediction model to determine the user's next request, and the model learns the user's behavior from previous requests. And the predicted page is then preloaded. There are 4 main topics we have to address. The first one, preloading. How can we do it? How can the browser preload data? And also the prediction model. We need a model which can be trained with user activities and predict the next step of a user. Then we want to integrate the, let's call it feature, in an existing, for example, Liferay application, and want to use the feature. And the last but not the least part is data acquisition. We need a lot of information about the user's behavior and other things to train the model and to preload the data. The topic 1 was preloading. We are using resource hints standardized by the W3C to preload the content. There are small link tags added in the HTML document which instructs the browser to preload the data. Supporting browsers can handle the preloading process efficiently. I will show later what that means. And important one, preloading does not affect the loading time of the current page. Especially we use the resource hint prefetch, because if you know resource hints already, pre-render is not possible. I will show you later why. Prefetch downloads just a single resource. In case of an URL of a page, that means just the HTML document and not the whole page. So we have to know which images, videos, CSS files or JavaScript files are included in this page, in this document. Here's a short example. The typical head of a HTML document, and we add 3 resource hints, prefetch, to preload 3 images. If we now load page 1 without content preloaded, without the added resource hints, it takes about 24 milliseconds to load the page completely. If we load the same page with content preloaded, you can see it here. The page is completely rendered and displayed, and the browser starts to preload the images. The page itself is also rendered in 30 seconds, almost the same, milliseconds. Okay, if we now switch or navigate to page 2 without content preloaded, the browser has to load the 3 embedded images, and the total loading time is about 760 milliseconds, quite long. On the other hand, if we already preloaded the images, we can see here, the browser has the images already in his cache. He only has to load it from the cache and not from the server anymore. So this reduces the loading time to 54 milliseconds, which is a latency reduction of about 700 milliseconds, and that's quite a lot. The question was also which content can be preloaded, and here I have to say not everything. Especially HTML documents are not preloadable. I will show you later or in the next slide why this is so. And also CSS or JavaScript files can be a problem. Must not, but can. Why we can't preload the HTML documents? The navigation data which are used for training the model are acquired on server side. For the server, preloading an element, for example an HTML document, is seen like a site is requested, a typical navigation step. And also, if a document is already preloaded by the browser, it lays in the cache and isn't requested anymore from the server. So we don't see this. I have also prepared a small statement example. In case 1, the user is on user's current page is A. The browser has the instruction to preload B, and the user navigates to C. The model gets as training input the navigation step AB and AC. You can see here. If we train our model with the navigation step AB, it would be the wrong decision because the user has never navigated to it. To use the navigation step AC would be the correct decision. In the next example, number 2, the user is on the same on the current page A, and he navigates to B. Nothing is preloaded. To train the model with the navigation step, right decision, clearly. The third example is the user is on the page A, he navigates to B, and the browser already preloaded page B. To train the model, right decision. Okay, what could we do to address this problem? We could ignore preloaded requests or requests which are triggered by preloading. That would look like this. The preloading instruction or navigation step is ignored. So our decision is correct. But if we take a look at the third example, we would also ignore the navigation step which is preloaded but was correct, and that's the wrong decision. So the only way to handle with HTML documents is to ignore them completely from preloading. And that's also the reason why we can't use the resource in pre-render, because pre-render, as the name says, downloads and renders the complete page with all including images, CSS or JavaScript files. Okay, on the other hand, we have, especially in Liferay, very user-specific resources. For example here, a JavaScript file which is customized for the Firefox browser and for the language English. And if we have a user whose language is German and uses the browser Chrome, it would be the wrong decision to preload those files. So special data types, for example JavaScript or CSS files, are excludable by configuration and can be not preloaded. Okay, the next topic is the prediction model. Here we use a first-order Markov-Chain as a base for our model. It could look like this. You have the pages, which are the states of the model, and the transition probabilities between the states. For example, here there's a 50% probability that a user switches navigates from home to end, which means he's leaving the page. So we need a model which learns the structure and transition probabilities, and therefore we need algorithms to adding new pages, new transitions, and update current transition probabilities. And the model is trained with user activities, which are navigation steps, for example, from page 1 to page 2. Okay, here we have a challenge. Which website, today's website, is static and doesn't change? Not a single one. I do not know a single one. So the challenge is websites change over time. That means we need something like continuous adaptation. Our model has to adapt over time. And we're realizing this by aging observations. The typical transition probability is calculated by dividing the number of transitions from, for example, from A to B by the number of transitions with the source A. And there you have the transition probability. That means you have two counters, and with every observation of a navigation step a user makes, the transition probability is adapted. But that's not enough. We need, as I said, aging observations, which means an observation made today is more important for the model than an observation made, for example, 2 weeks ago. We realized it by adding, by using a growing weight, which is added to the counter instead of just adding one. The weight itself depends on the timestamp, and a specific parameter delta defines the aging rate. For example, you set delta to 2 weeks, and the model ages in a specific speed. But there's a problem. If you infinitely often add a value to another value, the value itself will grow infinitely high. We cannot store that. That's bad. What we do is we implemented a division algorithm which divides the counters on every delta days by delta. And the weight itself, which is added, is calculated depending on delta. For the formula lovers here, this is the formula. Okay, another problem is, let's say you add one page to your web page, to your portal every day. You have also an infinitely growing number of model states, and we have to address that also. So we have to delete no longer relevant transitions or states from the model. That's quite easy. An irrelevant transition is a transition with a probability below 1%, which means below 0.01. And an irrelevant state is a state which is not part of a transition, because we deleted all transitions which are not relevant, and the states which are not part, we can ignore, we can delete. Okay, now we want to integrate the model in our portal, in our web application. Therefore, as I said, we have to find the relation between a page and its resources. There are two ways where we can realize this. The first one is we are learning the page resource relation with the header referrer. In the referrer header from a resource, for example, an image, there's the address where from which page the image is requested. But here you have to trust me, that's quite impractical. The other way we can address this is we parse the successor page determined by the model, and find or extract the resources which it contains. There's also a theoretical drawback that delays the process duration, the preloading process. But we are requesting the successor page from localhost, which typically lasts just a few milliseconds. That's okay. That's not significant. Okay, how do we implement this? We are using a JEE Filter. It allows us to manipulate the response before we send it to the user. And we have 5 simple steps to realize this. Our model determines determines, sorry, the successor of our currently requested page A. The successor B is loaded and parsed for resources, and the resources which are found for this, the resource hints are added to our current document from page A. Then page A is delivered to the user and the browser renders the page. If it's fully displayed, the browser begins, as I showed in the example, with the preloading phase and downloads the resources. And that's all. But applications are different, and so is the user's behavior. So we have to, create parameters to adjust the model a little bit. There are two important parameters which are configurable, and the first one is pmin, which means the minimum transition probability requested for preloading. So let's say you set it to 0.5, 50%, then the preloading starts only if the decision is the decision probability is minimum of 50%. You could set it to 100%, but there wouldn't be much preloaded. Okay, the other parameter is cmin. If you add a new transition to the model, it would have a transition probability of 100%, and so it would be preloaded. But this decision would be wrong because we don't have something like a training phase. So the cmin parameter defines this training phase. It says a new transition has to be observed, for example, X times before the new transition is preloaded. So it defines the length of the training phase. Okay, the question is now, how do you set these parameters correctly? I will address that later. The last topic was the data acquisition. To have a reliable model, we need reliable user activity information. The simplest approach is we cluster our requests by IP address or the session ID, sort them by timestamp, and so we have our navigation steps. I will show you a quick example why this is not correct. Let's say a user navigates from A to B and opens a new tab C. He's currently on two different pages, B and C. Okay, the next navigation step is D. We cannot say which was the source of the navigation step. It could be B, it could be C. If you use the header referrer again, we can say it easily. And for example, it's B. It stands in the referrer where the navigation requests comes from. But what if in step 4, if the user navigates from B to C to D and also from C to D, and it's currently has currently opened the same page twice, then we have a request to page E with the referrer header D, and that's the problem. We cannot say it for sure. Okay. Yeah. So the header referrer is the only reliable source of informations for the user navigations. And because we cannot use longer navigation paths, only the last steps, we have to use the first order Markov-Chain. If we want to use a higher order Markov-Chain with something like a history of the user's navigation, we have to find a reliable source of the navigation path. Navigation path, which we don't have. Okay, and also important to note is that when a user leaves the page, that's also an important navigation step for the model. What we also need is a reliable source of states for our model. But a URL is not only the path and the host. It's also, for example, the query or the fragment. The fragment is not important. We can cut that off. And also, the query makes a lot of problems. So, yeah, it could contain a timestamp. It could contain form data. It could contain everything we can imagine. So the simplest solution is we cut it off. It worked quite good. Exceptions are configuratable possible. Okay. Now we have a lot of requests which are sent to the application server or the web server, but we don't want to have the irrelevant one, or we want to ignore them, the falsifying ones, which are relevant. Every page request with the HTTP method get and the status code 200. Which we don't want to have are resource requests. They're not interesting for us. What requests also should be filtered are robots. They have no human nature, as the name says, so we have to get them out. How could we do that? Luckily, there's the robot exclusion protocol, which says that every good robot have to access the robots.txt file before he enters the page, the portal, the website. And so we can find out who is a bot and could exclude them. Yeah, more difficult are, let's call it bad bots. They don't want to be seen as bots. They try to hide their identity. Yeah, so all in all, we need a lot of information to train our model, which are listed here. How can we acquire them? We used a custom access log valve. It allows us to get all the necessary data we wanted to have. Also, we could filter the requests, for example, the bots, and we could process or adjust the data if necessary. And as last step, we can train the model immediately and don't have to store the log data, the request data. And that's a huge advantage because it could be a lot. So here I displayed the complete process of training and preloading. On the right side, you see the 5 steps which I described for preloading. On the other side, you see the training phase. After the response is sent to the user or to the browser, request and response are gathered by the log valve and are filtered and used for training. Okay, I can tell a lot, but we also evaluated our model. So we used real-life data of 4 weeks to train and let a model predict our successes. And in 76% of all cases where the model determines the successor, and which with a higher probability than 50%, the prediction was correct. And that's quite a good value. To evaluate the latency reduction, it is a bit complicated because it depends on network latency, it depends on the amount of preloadable data and the idle time of the browser and many more. But we have seen in our example, just by preloading 3 images with, a bit bigger, a bit higher size, we could reduce the loading time about 700 milliseconds. And every time something is preloaded, which is requested, which would be requested by the user, there is a latency reduction. If the data or the resources are not requested, nothing happens. Okay, it also, the evaluation shows that that not all portals or websites are suitable for preloading. For example, if you have wide sitemaps, so you have no clear user paths, or your portal or your website contains a lot of navigation pages, you have very low transition probabilities. And also, if you have a lot of one-page visitors, for example, the people are searching something in Google, they go to your site, view the content, and leave it immediately. There is no navigation step which could be used for training. And so, yeah, that means you have to evaluate the portal, the website, before you use the preloading function. This is done very easy. You deploy and configure the module and run it in evaluation mode. Evaluation mode means that preloading is not enabled, and the module collects all that and stores all the data. So you have to, you can train, or you can test different parameter configurations and choose the best one. And then you have to decide whether it's worth it for your portal or website or not. And you can do that by having a look at the preloading rate, which says how often is something preloaded or how much is preloaded. And if the rate is high enough for your then you can activate the preloading function, and the module starts to reduce the latency for your website. So, this presentation was just a brief overview. We have only 30 minutes, which is quite a few time. So I can't tell everything. Some of the additional challenges we overcame is, for example, detecting the users leaving our website, or the bad bot detection I already mentioned, and many more. We have about 2 minutes left, so there is room for questions. But if you have further questions, you can visit me or my colleagues at the Unymira booth in the front of the building. So, thank you for your attention. Are there any questions? Okay.